Greetings, Chem 244 students. My name is Dr. Ed Brush, and I'm going to be, let me first start off by welcoming you all back for the spring 2017 semester. For many of you, this will be the first time I'll be seeing you since I think all of you had Dr. Wartuk for Organic Chemistry 1 while I was on sabbatical in the fall semester. And I'll be seeing you all this first week of the semester as we start up the second semester of Organic Chemistry. What I want to do in this video, besides trying to introduce myself, is to do a little bit of a review on something that's going to be very important in both semesters of Organic Chemistry, but in particular in the spring semester. And this pertains to understanding how to write reaction mechanisms in organic chemistry. So I know that for many of you, your response to reaction mechanisms is probably this. And hopefully by the end of this video, we'll flip that frown upside down. But I want you to first understand why it's important that we do understand reaction mechanisms. First off, understanding reaction mechanisms gives us a very good and clear idea of how covalent bonds are being made and broken. Secondly, we get a very good idea of the role of catalysts. We'll be reviewing that, but a catalyst is something that is neither a reactant, it's not a reactant, it's a reagent. It lowers the activation energy, but it is unchanged, and as such a catalyst typically will cancel out in a mechanism. Okay, we need to be able to see that and understand that. Also, by understanding one mechanism very clearly, the mechanism for one general type of a reaction, this leads to an understanding of literally thousands of different organic reactions. For example, acid-base reactions are critically important in organic chemistry. If you understand the mechanism of one organic acid-base reaction, you literally understand thousands, if not tens of thousands or millions of different reactions. And finally, and this is relevant to my research, but by understanding the chemical mechanism of a reaction, it also helps you to understand or even predict the mechanism of drug action. How drugs and other therapeutics act in the body is based on chemistry, and in many cases organic chemistry. So if we understand how an organic reaction is occurring in a beaker in the lab, this gives us insight to how an organic reaction or how a pharmaceutical or a therapeutic agent is actually behaving in the human body. All right, so what we're going to do is we're going to go through an example. And this example is going to be very similar to example 5A that's going to be on the first worksheet that you're all going to get. And what we have here is an alcohol reacting with an acid, and we see that the OH group of the alcohol is being replaced with a halogen, with the Br. So what we have here is a tertiary alcohol. We have HBr, which is both an acid as well as the source of a nucleophile, and the net effect of the reaction we're looking at is actually an SN1 substitution of an alcohol. And it's one of the other things that you all will be reviewing on the worksheet that you're going to be getting. Alright, so again, a tertiary alcohol. The OH group is a poor leaving group, so it has to be activated. That's why we need an acid in order to protonate the OH, so it'll leave better as water. And then we have Br-, which is a good nucleophile. And again, since the alcohol is tertiary, this leads us to believe we're going to have an SN1 substitution, meaning that we're going to be going through a carbocation intermediate, or also called a carbonium ion intermediate. So whenever I give you a problem where you have to write the mechanism, you're always going to start off with a balanced net equation, which is what you see right here. And that'll become relevant later. All right, so balanced net equation. Now, in Dr. Wartu's class, you guys probably approached the mechanism using by what I call the flow chart method. All righty, so here we have the start of this mechanism. We have our alcohol, we have our acid, and lone pairs on the alcohol. Curved arrow is going to grab the proton. The HBr electrons have to be left behind on the Br. Br is more electronegative, so the electrons are going to flow in that direction. And the curved arrows tell us that we have a bond being formed between the oxygen and the proton, and a bond breaking between the proton and the bromide. This leads us to our protonated alcohol, ready to leave, and the Br minus. Okay, so the curved arrows show us how the electron flow, how bonds are being made, how bonds are being broken, and we get our intermediate products. Now, in the second step, the leaving group is ready to leave, so those electrons are going to go towards the positively charged oxygen. That bond breaks, giving us our tertiary carbocation, and water is a byproduct. And then in the final step, this carbocation wants a pair of electrons, so the bromide that we formed up here in this step, an intermediate, will come in, grab that carbocation, and we're going to form our final product. All right, so there's your step-by-step approach, or excuse me, the flow chart approach to writing a chemical mechanism. Now, this is perfectly fine, but in terms of teaching students to understand organic chemistry, I really don't like this method. So we're going to be using something a bit different in my class, and it's a method that I call the individual balanced equations. All right, where each of those three steps that we saw above are going to be written as individual balanced equations, and there are advantages to this. All right, so let's get started. So we start out with our reactants. Again, the OH group is going to grab the acidic proton. That's going to form a bond, and since hydrogen can't have two bonds, we got a pair of electrons being left behind. Arrow to our products. We form our protonated alcohol. Don't forget the charge. And, of course, the Br minus. Now, this is the way that you were taught to work with chemical equations in Chem 141 and 142. You write balanced equations where you have mass balance on each side and you have charge balance. We have net neutral on the reactant side, and if you add together the negative and positive, you have net neutral on the product side. That's step one. Now we label step two. Step two, we take the product from the first step, which we call an intermediate. Intermediates are not going to be your final products, they are intermediate products. And we have made the OH a better leaving group. So now we show the leaving group leaving. We get our tertiary carbocation and water. Again, we have a balanced net equation. And in step three, we again take our intermediate from the previous step, the bromide, the nucleophile, from step one, and we form a new bond and complete our SN1 substitution. Okay, so that's the step-by-step approach. Why do I like this? Well, first off, we're looking at balanced equations. And as chemistry students in a chemistry class, you should be able to balance equations. Secondly, you can clearly see what the intermediates are. It's much more difficult using the flowchart method to see and to really clearly see the intermediates. Third, we can label the role of each step. So the first step is an acid-base reaction. And its purpose is to activate the leaving group. The second step, the leaving group leaves. And in the third step, the nucleophile adds. So if you're just learning a new reaction, when you write the mechanism, sometimes it's helpful to write the purpose of each step of the mechanism over the arrow. Occasionally I might ask you to identify the rate limiting step, okay, which we can also do. Where do you think the rate limiting step is here? Rate limiting steps are usually when a covalent bond breaks. So I'm going to say that step 2 is a good shot at being the rate limiting or the rate determining step. We don't have a catalyst in this reaction, but when we do have a catalyst, we'll be able to much more clearly see that catalyst in using the individual balanced equations. Now there's one last thing I want to point out, and that is what happens when we add up the steps of the mechanism when done in this way. Let me just scroll down a bit. Okay, well, to add up the steps, get a different colored pen, we see what cancels out on the reactant and product side. So for example, that will cancel out with that. Intermediates typically cancel out. The bromide on the reactant there cancels out with bromide as a product here cancels out with bromide as a reactant. And this carbocation intermediate cancels out. So what do we have left? Okay, we've got reactants, we've got the water, and we've got the brominated product. So if we write those out, what do we have? So this is everything that's remaining after canceling things out. And if you have done your mechanism correctly, when you cancel out the individual steps of this mechanism, you should end up with the balanced net equation for the reaction. And this is a great way of checking that you've done your mechanism correct. So hopefully this is helping you. And as you're doing the worksheet number 1, you're going to find that this might be a better approach to doing and understanding mechanisms. Great. Be seeing you all soon, and that is the end of this recording.